Hi everyone, welcome to the lecture for 4.8 on L'Hopital's rule. So L'Hopital is from the Calculus 1 book, but it really comes into play for improper integrals, which is the next section in chapter 3. So L'Hopital's rule is just a way to handle limits of indeterminate form. And so our indeterminate forms are 0 over 0, infinity over infinity, but we also have things like 0 times infinity, infinity minus infinity, 1 to the infinity, and all this other good stuff. So these indeterminate forms, it may feel like, okay, why can't we say infinity over infinity is 1? Or why can't we say infinity minus infinity is 0? It's because infinity is a number, it's more of an idea, and there are different sizes of infinity. Functions can go to infinity faster or slower than other functions. Like, for example, exponential functions completely obliterate a polynomial function. Even though polynomials and exponentials can both go towards infinity as x approaches infinity, one of them gets there a lot faster. So to handle that, we have L'Hopital's rule. The first case we're going to look at is 0 over 0. So if we have a limit where the numerator and the denominator are both going to 0, what we're allowed to do is take the derivative. So in example 4.38, we can see that in both A and B, if we kind of look at the limits of the numerator and denominator separately, we're going to get a 0 over 0 case. So for A, if x goes to 0, then this would become 0, and then this would become 0 as well. So what we're allowed to do is differentiate top and bottom separately, not using the the quotient rule. And when we use L'Hopital, it's appropriate to put a little LH over the equality symbol to alert the reader that L'Hopital is in play. So if I take the derivative of the numerator, I'm going to get positive sine of x, and the derivative of the denominator is just 1. So now I reevaluate the limit. As x goes to 0, sine of x goes to 0. So this becomes 0 over 1 because, yay, sine is continuous. And so this limit is actually just 0. With B, we follow the same process. As x approaches 1, sine of pi x will approach 0, and ln of x will also approach 0. So we are in position to use L'Hopital. Something I see that happens a lot with L'Hopital in terms of notation is that people forget to keep writing the limit notation. Like, so even though we're applying L'Hopital, we still have a limit on the other side. So the derivative of sine pi x is pi cosine pi x, and the derivative of ln of x is 1 over x. So these are both continuous at 1. So what I'm going to get here is pi times cosine of pi, which is -1, over 1 over 1. Which is just 1. So this is going to be negative pi. So notice once I evaluated the limit, I stopped writing the limit notation. When I'm still haven't evaluated the limit, I have to write lim x goes to whatever. I also can do the same thing when I have infinity over infinity, the exact same process. So in example 4.39, you'll see that A, this is very reminiscent of algebra days when we were asked to evaluate horizontal asymptotes, where we would look at the degree of the polynomials in the numerator and denominator and make our conclusions based on that. But now we can handle it a little bit of a different way. So if we take the limit as x goes to infinity, we know we're expecting it to be 3 over 2. But just to kind of get the mechanics down. So as x goes to infinity, these both go to infinity. So we can apply L'Hopital. And we're going to still write our limit notation, but just take the derivative of top and bottom. So it's going to be 3 over 2. The limit of a constant is just the constant. And then for b, we have the limit as x goes to 0 from above of ln of x over cotangent of x. And this is going to go, as x goes to 0 from above, this goes to negative infinity and infinity. And the negative doesn't change anything. So we could even have a constant. It's still in that indeterminate form, infinity over infinity. So I'm going to take the derivative of top and bottom separately. So I'll get 1 over x, and then the derivative of cotangent is negative cosecant squared x. And so from here you might think, okay, well, this is still going to infinity over infinity, so I'll just take the derivative again. And all of a sudden, you've kind of turned down this path that will frustrate you, because what's going to happen is it's getting worse. Like it's getting uglier. It's still going to be infinity over infinity. You're just like, hey, what's going on here? So if that's happening to you, if kind of like when you do integration by parts, like if you're just like, oh my gosh, this is like making things worse, that's a tip off to you that you may want to rethink a previous step to see if you can kind of change course. So this is worse. I'm not happy about that. So let's change gears. Let's take it from right here. Instead of writing 1 over x, negative cosecant, let's write it like this and see if we can do some maneuvering. Maybe it'll make something look better. So cosecant is 1 over sine. So this is going to be negative sine squared x. And from here, I'm going to write this as my fraction, because right now we only have it as 0 over 0, infinity over infinity. So I need to get it in that form. So I have negative sine squared x over x. And I kind of reassess. This will go to 0 over 0. So I know I can apply L'Hopital, and I get negative 2 sine x cosine x. See, I did it. I didn't write my limit. I knew it was going to happen. Equals the limit as x goes to 0 from above of negative 2 sine x cosine x over 1. And as x goes to 0, this will become 0 over 1, which is 0. Right, okay, sorry. I'm just making sure I'm doing this in the right order. So the next example here is 0 times infinity. It looks a bit different than infinity over infinity, but let's think about this as infinity over 1 over 0, right? That would be the same thing as 0 times infinity. Of course, I'm talking nonsense because these things aren't really numbers, but just structurally, bear with me. 1 over 0 is infinity, right? So this is really an infinity over infinity form. And so that's the idea for working with these. So if we have the limit here as x goes to 0 from above of x ln x, then we should write this as ln x over 1 over x, right? And so these are equivalent algebraically, and it gives us the added benefit of putting it into this form of infinity over infinity, so we can use L'Hopital. So applying L'Hopital, we're going to get 1 over x over -1 over x squared. And so my next step would be just to clean this up a little bit. I'm not evaluating a limit or using any fancy calculus, just an algebra. So this is just -1 over x. And as x goes to 0 from above, this becomes negative infinity. So that's our limit for example 441. And that's always the trick when you have 0 times infinity, by the way. Like, always do that. Make one the denominator by flipping it 2 times. Okay, infinity minus infinity is probably the second most challenging one. And by challenging, I mean fun. So the idea is to find a common denominator and just combine the fractions. So the way that we'll do that is find the common denominator of x squared and tangent of x. And we may be used to finding common denominators of things that actually have common factors, you know, like a third and a 12th, or like an 8th and a 6th. But it's always the case that you can multiply the two denominators together to form a common denominator. It may not always be the optimal common denominator, but it always works. So the idea is then to say this is tan x over x squared tan x minus x squared over x squared tan x. So we can see that our common denominator is just x squared tan x, which was the product of the two. So I'm going to just combine everything together, and now I'm ready to consider the behavior as x approaches 0 from above. So, okay, tan of 0 is 0. 0 squared is 0. So this becomes 0 over 0. Yay, because I can use L'Hopital's rule and just take the derivative. So again, limit as x goes to 0, but this time taking the derivative, so I'm going to get secant squared minus 2x over, and now I have to use the product rule. So this will be 2x tan x plus x squared secant squared x. Then as x goes to 0, so secant being 1 over cosine, so this goes to 1, this goes to 0, this goes to, so like x being a factor in both of these terms means that they both go to 0. So this is 1 minus 0 over 0. So things of this nature, 1 over 0, they go to positive infinity. Okay, now the fun stuff. So, fun fact. If we have I'll just write it like this. The log of the limit is the limit of the log. And the caveat is that provided the limit exists. Right, so if I wanted to say take the limit as x goes to infinity of x to the 1 over x, I would say, I'm not really a huge fan of this exponent, which is why I'm a huge fan of logarithms, because logarithms are awesome. They're undervalued, underappreciated. And the reason we like them for this particular setup is because algebraically, they have the property that they pull the exponent down in front. So the first thing we're going to do is you're going to assume that the limit exists. We don't know that it exists yet, but we're going to assume that it does. And we're going to say, let L equal the limit as x goes to infinity of x to the 1 over x. Then I'm going to take the natural log of both sides. So ln of L equals ln of the limit as x goes to infinity of x to the 1 over x. And so now the log of the limit is the limit of the log. So I can interchange these to bring ln inside, which is great because now my natural log will help pull that 1 over x down. So I get the limit as x goes to infinity of 1 over x ln x, which I'll write in terms of a fraction. So this goes to infinity, this goes to infinity, you get a car, and you get a car. Okay, so because we're in this indeterminate form, I can apply L'Hopital. I'm still haven't evaluated the limit yet, but I am going to take the derivative. So 1 over x over 1. Certainly as x goes to infinity, this is 0. So our limit is 0, right? No, it's not. The natural log of the limit is 0. So be really careful with this step. What we have is that ln of L equals 0. So if the natural log of something is 0, that something has to be 1. If you really don't like thinking about that conceptually, just take each side to raise it up or exponentiate it with base e. E to the natural log is just itself because they're inverse pairs, so L equals 1. That's how you can prove it in a court of law, but you could also just like remind yourself that this is the case. Left side easy, right side, I don't know, litigious. Let's do another example like that, and then that will conclude our 4.8. So same thing. When I have that exponent, it's my tip off. I'm going to assume the limit exists. I'm going to call it L, and I'm going to say let L equal the limit as x goes to 0 from above of x sine x. Then the natural log of L is the natural log of the limit. And the log of the limit is the limit of the log. Then we exploit the log to fetch the exponent down for us. So then I have the limit as x goes to 0 from above of sine x ln x, right? But this is going to give us a 0 times infinity thing. We know how to deal with that. What we're going to do is we're going to take 1 over sine. So this is going to become the limit as x goes to 0 from above of ln of x of 1 over sine. And this definitely goes to infinity over infinity. But we could also write this as the limit as x goes to 0 from above of ln of x over cosecant of x, right? So again, I didn't apply L'Hopital. I just rewrote 1 over sine of cosecant. It's still the case that it's infinity over infinity. Now I'm going to apply L'Hopital. So I get 1 over x over, the derivative of cosecant is negative cosecant cotangent, So this is infinity over infinity, and we're kind of back to that same place that we were before. Let me see if I can scroll up for a second. Yeah, this guy, right? So this is hideous, and we didn't like going down that path. And our plan was to kind of diverge on this pink path and see what we could do by simplifying the trigonometric expression. I'm going to do the same thing here on our last example. So just doing some algebra. I have 1 over x times negative sine x tangent x. So I'm going to write this as a fraction, negative sine x tan x over x. And as x goes to 0, this will go to 0 over 0. I'm very happy. I apply L'Hopital. I have to do the product rule on the numerator, which is no problem. I still have yet to evaluate the limit. So I'm going to get negative sine x times secant squared x minus cosine x tan x over 1. And as x goes to 0, this goes to 0, this goes to 1, this goes to 1, this goes to 0. Well, guess what 0 times 1 is? It's still 0. So 0 over 1, 0. That's it.